Okay, so this is partly a technical talk, partly a talk about what we're doing in the city of Cambridge to try and build some technical underpinnings for the smart city of the future. The project in Cambridge is branded Smart Cambridge, you see in the top right-hand corner. And the technical context is going to be the software I've been using to try and build this sort of real-time sensor information flow underneath it is Vertex, and that is the technical theme in this talk. And there are pages with code on it, just to warn you ahead of time. In the background is web servers for the longest time have basically relied upon two basic commands, get and put. It's sort of a user request says, I want to get this web page, therefore receives a web page, and then subsequently may interact with the page and click a button, and that involves in data being passed back to the server and executed on the server in some way, and data typically being put into a database. Everything a web server has done really for the past however many years it's been pretty much fits that model. There's nothing wrong with that model. What I'm trying to make clear with this is that is one way of doing things, but it's not the only way of doing things. And in fact, for some modern websites that you interact with without particularly thinking about it, that is not sufficient for those websites to work the way that they do. So that's the part I'm kind of bringing to the UIS, really. Okay, so all these applications, click to tax your vehicle or click to order something, they're all operating the same way. It's a request followed by a response. It goes into a database. Even if somebody else wants to subsequently see your orders, their thing is operating exactly the same way. They do a request, what orders do we have? That response comes back listing the orders on the screen. So it's the same basic mechanism. Even webmail, which emerged, is actually relying on the same get and post, which is why you tend to see webmail, as you're looking at the screen, it refreshes itself every 60 seconds or every 2 minutes, whatever it is. Basically, behind the scenes, the web page is doing another get for you. It's periodically doing a get just in case there's some more mail. Okay, I'd like to give a small personal detour just because it's fun for me standing up here, but it'll help you understand the angle at which I've been coming at this smart city development for Cambridge. And that's for 25 years I worked in the financial services industry. Banks do have those traditional request response systems. They have billions of dollars worth of those request response systems, like Oracle Financials. You click a button, put something into a database, somebody else then looks at it, processes it. But banks also have a large part of their IT systems match this diagram that you can kind of see in front of you. Information is flowing into the bank. It's being processed typically as it arrives. Derived information from that, the information what I'm talking about is things like the price of IBM stock or whatever, which is being updated. Subsequently, it arrives on the trader's screens you're familiar with seeing. But the point being, that entire process flow is event-driven from start to finish, and there will be quite a few different systems developed by different people in this flow. It's just every single one of those systems is capable of waking up in real time, receiving data that it didn't know it was going to get at that particular moment, processing it and then passing it on or storing it or doing whatever they're actually going to do. And as an aside, as a personal comment, running the IT department in an investment bank, you have to be a little bit careful that people that have grown up building request response systems and are surrounded by other people building request response systems can build up this idea that that's how computers work, not realizing there's a kind of a broader world out there, a variety of different models of information kind of flowing around. Okay, so trading applications aren't request response. The information arrives. You can't predict when the information is going to arrive. When the IBM share price changes, you didn't know that ahead of time. You'll see I have an analogous examples in the city, which is when a bus is going to arrive at a bus stop is, trust me, random. You want to apply real-time calculations to the data as you get it, not necessarily. In the old style thing, you'd run a batch job overnight, perhaps, that would add up all your invoices of the day. This message flow extends all the way to the user's workstation. That took a bit of a back step when we went to browser as the UI of choice. The browser isn't designed to deliver real-time information. It wasn't, anyway, designed to deliver real-time information. The user will update itself in real time. And actually, these banking applications, the fact that a trader has done a trade, so he looks at something on the screen, is itself real-time information. So that transaction that gets executed, in a traditional kind of banking model would get written to a database. Of course, it still gets written to a database, but the fact that this trader clicked buy 10,000 IBM, that itself is an event that now ripples across, in Merrill Lynch's case, I used to work, 10,000 systems we had, right? And this information is rippling through all of them, and we're trying to make sure each one does what it's actually supposed to do with the data. Okay? And actually, my last point here, 5. So message passing is a core architectural element in a system of this type. With a straightforward request-response system, the database really is the dominant theme. When somebody enters in a purchase order, what are we going to do with it? Right? And by far the most important thing you do with it is structure the data appropriately and store it in an actual database. Somebody else then subsequently is going to go, so what orders have we had for this particular widget? They are going to do a database query that will show the data. It shows how central the database is. And of course, on these real-time systems I'm describing, of course you have databases, but they're not quite as, in fact you can have many of them if you want, they're not quite as central as you'd assume. Another personal diversion, this is just a fun part, I spent 3 happy years doing a PhD at the Computer Lab here at Cambridge. It was to do with AI and logic and parallelism. They were described in 1995 as the 3 least glamorous areas of computer science. But you could, if I'm trying to explain what I was doing to friends, which I learned to do over a period of years, it equated to searching a maze. Okay, so you're searching a maze, how would you do it? The challenge I had is, what about if the maze was the size of the solar system? Okay, searching it suddenly gets a bit harder. But the good news is, you can have potentially a very large number of helpers, i.e. computers. My model was how to use the internet as an aggregated AI machine, specifically in the area of logic. And what you do is each agent that is searching, you give them a piece of the maze to search. That's all realistically you can do. They search their piece of the maze. Then they end up in one or two states. Either their work is done, they've got to the end of that piece you told them to search, in which case they want to communicate with other helpers and say, I've finished my search. Or they're kind of still searching. And what you do is, some of these agents search. When they become idle, they kind of sit in a huddle until some others have been idle. And when you've got a sufficient group, that group of idle workers then want to interrupt another worker and say, you're still busy, you're searching the maze. Who knows what's ahead of you? Split your work up, and we're going to divide it between the 6 of us, let's say. Now, 6 people now divide up the work that person was doing. And you do that iteratively as this maze gets searched. Do any of you guys care about that? Probably not. But it's to illustrate that there are different system design types. What they have in common, trading and that AI platform, actually have a characteristic where it's helpful to be able to model what's going on in your head is a particular thing. I know this is generally true anyway. You're kind of picturing agents talking to each other. Saying, I'm busy, are you busy? And then and you have a defined protocol between your agents of, would you do this piece of work for me, or would you process this data? So it looks more like a message, it's real time, it is message passing. Agent-based programming or actor-based programming are very trendy now. So, this idea, you have an actor acting on behalf of a particular, it does a particular job. It receives messages, doesn't think about them too carefully, but it does something with them. Okay, and that doesn't preclude any of the stuff with which all of us are most familiar with. You've got a transaction, the application code looks at it, decides what to do with the data, and then writes it to a database. All that stuff is, of course, still there. Okay, Smart Cambridge, we needed a interface the public can use. So we're talking about in a city, you have sensors. The richest source of sensors we have at the moment are the position data dongles that are on every bus in the region. They're transmitting every 30 seconds, roughly, real-time data of where they are. There are plenty of other sensor types. Meters, water meters from the water board themselves tend to be remotely readable. Air pollution sensors, we're putting some out in Cambridge at the moment. The fact that we have hundreds of millions of what I used to call drive-by logons to the wireless access points in Cambridge. People wandering around, they're generating these events on the wireless access points constantly. There's all this kind of traffic taking place. The city of the future, cities will get more digital. the city of the future will become increasingly dependent upon its digital platform. And they will be processing more of that kind of data to both inform the public, which is the diagram you see on the left, like where's my bus, or what time will I get to Addenbrooke's, or how will I get to Addenbrooke's, or planners will need to be able to look at this information to make much more intelligent decisions about investments to be made or modifications. But also, it's not written on this slide, the city of the future will adapt based on this information. So at the moment, infrastructure in cities isn't really connected. Traffic lights aren't connected to each other. They're not connected to the traffic sensors apart from in their little local loop. But you can imagine the city of the future with typically autonomous cars in it, I suppose. But traffic redirecting itself according to bad things will still happen. A car will catch fire on Hills Road, but the traffic flow will adapt and flow itself around it. Okay, so they're the requirements of the platform. And I'm here to talk about Vertex, which is the Java virtual machine platform of choice today, if you were focusing in this particular area. So web servers, I mentioned before, are request response. Works really well if you've got 10,000 users. You have 10,000 users on a website, all doing a request response. The way that web server works, the way you make it so it works as opposed to fail, is you make sure you respond to that request really quickly. So one user comes in, so 10,000 users over a period of 10 seconds might all ask us something, but actually those requests are all being interleaved between each other and they're all being responded to. And so long as you don't just get overloaded and run out of time, you can just respond back quickly to everybody. It's like basic multitasking. Everybody feels like they've got a dedicated web server, but in fact, the responses are being replied back. And it's not that difficult to build a web server that can respond to, say, 200,000 web requests a second. Okay, it's kind of reasonable. That model gets killed when the end user wants a long-term connection to the server. So what happens is your connection to BBC News lasts very briefly. You said, give me the news, it gave you the news, and then it did that in milliseconds. And then as far as it is concerned, it's no longer allocating any processing time to supporting you in any way. So it's really quite efficient. Whereas if you build the kind of web application where the user's interaction with it is more consistent, like, I don't know, you're watching a bus moving on a map, right? Your connection to the web server is an ongoing permanent connection. It's not too bad with buses because they're only telling you where they are relatively infrequently. But the idea is there that you want to maintain a connection to the web server. And at that point, you are holding open a very precious resource on a web server like Apache, a traditional web server, that kind of thing. They're not designed for, crucially, these more recent developments like WebSockets to the browser client. So people have developed applications using WebSockets as an example of where you can have real-time communication back and forth between the browser and the server. And for the past small number of years, 3 years, 4 years, I'm not sure, something like that, they've relied upon a web server called Node.js as the web server you use, which can cope with thousands of permanent connections to its clients. Okay. Vertex, part of the inspiration for Vertex was from Node. And Node, the way Node was implemented was these WebSockets were implemented in the browser first. Okay. Very talented group of people working on Netscape, or not Netscape, Mozilla, Chrome, whatever. They developed these WebSockets in JavaScript, and there was no server-side implementation of them. So it's a bit like the Humber Bridge, kind of didn't go anywhere. And the first web server to implement the other end of these WebSocket connections was itself written in JavaScript, which made it easy for them to do. And that was Node. So you'll hear Node is quite trendy. If you haven't heard of it, it's a good buzzword to have. Vertex was inspired by Node, and it's based on what I would consider a more robust, engineered server-side platform, i.e. the JVM and Java. Okay, and the trick for these long-term connections is every function call you make in normal programming. Say you were to issue a command, copy this file, a bit like when you type it on a command line. You type it in, wait for it to happen, and the command line doesn't come back until it's done it. So when the command lines come back, you're confident that copy has now taken place. That's a synchronous method of programming. What Node.js has and what Vertex has is every function call is basically do this, comma, so you've got a normal argument, like square root this number. It doesn't do it at that micro level. It's more things like file I/O or web services. But it basically says, here's the arguments, do this, comma, and then you add an extra argument at the end, which says, when you're done, call this function telling me you're done. So I've got no idea how long you're going to take or when you're going to do it. And so what that means is non-blocking, is your code can kind of crack on, and then all this code is executing asynchronously, not holding up resources serving the user. Okay? And so Vertex has got quite a comprehensive library of those key things you would actually want to do. It's illustrated here. So, for example, if you set a timer, you say every 1,000 milliseconds, call this callback. Or if you create, that's the first example. The second example is if you've created an HTTP server, i.e. a web server, basically you say, I'd like to add, the web server is now up and running, it's on port 80 or whatever it is, people can do a request, and what you're basically saying in your code is, I don't know what's going to happen, but when a request comes in, call this function. Right? That's asynchronous code. You're not sitting there waiting for the request to come in. You've just assigned a callback to happen. And actually, if you've done browser-side programming, JavaScript has really got a lot of this style of programming, because you never know when a user's going to click. So in your JavaScript code, you tend to write it in that way. You can say, when the user clicks, do this. I don't care when it happens. And Vertex extends that to the server side. When a request comes in, do this. When a message comes in on a socket, do this. When a file I/O completes, do this. Okay, let's talk about what Vertex actually provides. And really, you can write a simple hello world. It only has to be a few lines of code. But the basic building block of Vertex is a package of code called a vertical. And you write your code within that vertical. And the idea is a program you can launch and kill. Okay, and when that program launches, as you'll see this develop, behind it, the Vertex library provides a number of capabilities, crucially including message passing between your verticals. So within your vertical, you can tell the vertical start yourself, or you can say stop yourself, but also a vertical can decide, I will send a message on something called the Eventbus. And you can also, in the same way as you're saying, here's a web server, if a request comes in, do this, you can kind of say, listen to the event bus. If a message comes in on the event bus matching this pattern, call this function. Okay? And at that point, your vertical just sits there waiting to do what it's being triggered to do by events occurring. Okay? So that's the basic vertical. And I'm going to summarize, there's sort of like 4 probably, I don't know the exact number, basic principles of Vertex. That's one of them. Okay? The event bus I've mentioned, that is the fragment of code by which you listen to the event bus. You say, I'd like to listen to an address on the event bus. That's the concept used called news.uk.sport. If a message arrives on that event bus, call this callback. Okay? So now you can have multiple verticals. It's quite neat with multiple verticals because you can make them fit for purpose. You have a vertical doing what you want it to do. Typically, your platform can be quite robust if an individual vertical dies. Something I'm not actually planning on spending much time about at all, but something also that comes with this is you can spawn as many verticals as you like. You can spawn verticals of the same type if you like. You can tell the vertical when it launches, you are launching in high availability mode, and it will sit there with others of the same type that have been launched in high availability mode, and only one will respond to the messages, but they will detect if the other messages other ones have died. The event bus can be local to a vertical, local to a group of verticals. It can be local to a Java virtual machine, or it can span Java virtual machines running on the same server, or it can span servers. All of those are just configuration choices when you set up a bundle of these things. All will become clear when you see what we've done for the Cambridge City platform. Okay? So verticals, event bus. An important part of the Vertex library is a web server. And the clever thing about it is it's a non-blocking web server. So it's designed from the ground up to support socket connections to other servers or WebSocket connections to browsers without getting clogged up. Okay? When you see, if you look at Vertex on the interweb, type in what is Vertex, you've got verticals, number 1. Number 2, you've got the event bus. Number 3, it's non-blocking. as you've heard, and you've got APIs for each of these key things I'm describing under item 3 there. It has multi-language support, assuming those languages run on the JVM. I'm less convinced that is that key, I think. It does do it, so it's polyglot is the term that it's used. It's a feature that's bigged up with Vertex. I'm not sure how important it is. In other words, if you're going to build something, choose the language you're going to do it and stick with it. I would choose it if you're programming in Java. And by the way, if you do have blocking code, there's no getting around it. Like you have to do a computation and that you know is going to take, something comes in, you're going to do something for 10 minutes. It provides these sort of much more general purpose worker threads that don't block the event loop, which is analogous to what you'd start with in something like Apache. Apache is designed to have worker threads for servicing web requests. And you can actually say, dispatch this piece of work, but use a worker thread. Keep it out of this non-blocking, very lightweight. So it's designed, for example, a web server could support tens of thousands of users. The message bus is designed to support hundreds of thousands of messages a second. Okay, and to put it in context, our use, so we have, we've got about 1,000 buses, we're getting the data every 30 seconds, processing that data. It does build up. We now have something like 1.5 billion data points of where these buses have been. But in terms of message rate, we're at a tiny fraction of what the platform would be able to support, i.e. the starting point is 1,000 messages every 30 seconds. And we're actually then creating derived messages from those. Okay, so here's the Cambridge Smart Platform, which has got, this isn't Rita, the Vertex piece I'm talking about, this is the overall program. We are aiming to deliver a suite of applications. We're talking to a variety of third parties. There are people within the university, plus there's some things we're going to be able to do with the Rita platform itself that provide transport information in a way a normal member of the public could consume it. I'm not going to show you anything in that category today. This is a much more technical talk. But there'll be a range of those applications. Behind that, you need a real-time framework, particularly one that is capable of supporting a variety of this sensor data. You can buy an application, like CityMapper, for example, is a third-party company that produces web-based apps. You can see them on your mobile phone, tells you where the buses are and all that kind of stuff. They're only interested in the transport data. They're not interested in any other information. So we're aiming to build a platform with an architecture that supports that growth for the city of the future. With the right-hand side, you can say that the federated network systems, where we're adding air pollution sensors, or we'll add car park occupancy data, which will come in quasi-real time. And where we said there's got to be a user interface for the normal members of the public, there's also got to be a user interface for those people that look at this data in a more considered way. So you want to look back and kind of say, what was the traffic on, or what were the journey times down Hills Road, both before and after we built the cycle path? So it needs to do each of those things. Rita is the real-time data hub, that section in the middle. Okay, so I'm expanding that section with my talk. And they're Vertex verticals. Okay, so the first one, this is quite quick, is what can you build with Vertex? So the first thing I built in an afternoon was a feed handler, which receives data in real time. The company that provides us with this position data of the buses said on something like a Tuesday afternoon, okay, we negotiated for 9 months. And said, yeah, okay, you can have the data. I'm going on my annual vacation tomorrow if you could set your server up today. And, and at the time, I was assuming they were going to give us the address of their server. It's kind of the way you think about things, isn't it? Here's where you get the data from. But in fact, it's actually characteristic of it. This is event-driven. It's push. It pushes all the way through. So they want the address of our server because they're going to push it. Because it's only every 30 seconds, that is actually an HTTP post. The data is just posted to our website. And every 30 seconds, the location of 1,000 buses turns up. Okay, feed handler. That feed handler, by the way, does immediately archive the data just in case it gets lost at some point elsewhere in this system. It's not the definitive storage of the data. It's effectively a cache a persistent cache just in case something else breaks. And the feed handler does what you expect in a Vertex context, which is it publishes the data on the address bus, okay? There's a different Vertex vertical called feed player, and it looks like a slightly inverted version of the feed handler, which is it reads the database and can play back the data for any day or for any time period, you know, kind of from anywhere, which means the rest of the code actually, I can tell you from experience, is more fun watching feed player data than it is watching feed handler data, because watching buses go down Madingley Road is a really slow, you know, I can see, when the feed player, it can play back the data 50 times as fast, which is good. You're kind of seeing, does the system work? Okay, feed player, and these things are console. These are the names of the modules as well. Okay, so console is each of these modules in the system, each vertical, is also, you saw that kind of set periodic, you know, every 100 milliseconds do this. Well, actually, every one of them has got, each of these verticals has got 5 lines of code in it, which says every 10 seconds, send a message to this particular event bus address, system status, saying you're up. Okay, so they all do that. And there is a console module which listens to that address on the event bus, learns what's up, and paints it green on the screen, and starts a timer when it's done that. Because if it doesn't hear that that thing is still up in 15 seconds' time, it's going to paint it as down. Okay, so it's a kind of a simple mechanism, but it's an example of something we've done relatively easily with this style of programming. That's the key point. This one's particularly interesting in that there are quite a few ways of communicating from the server to the browser. That's a particular example. This is designed for server-to-server communication as well. But you can use WebSockets, you can use Ajax, you can use you know, a variety of those things. Actually, Vertex's library includes a JavaScript component just for extending the event bus. So this set of library, because you know, I said it was polyglot, you can, on the server side, you can write everything in JavaScript if you want. I wouldn't recommend it. I think Java's a better language. Once you get into your browser, you're in the JavaScript world. There's a small library provided, which basically, it's called the Eventbus Bridge. And it moves, you define in a configuration, you define what messages did you want to subscribe to on the event bus that you would like to forward to the browser client. Okay, it's not just broadcasting everything. And actually, if you want, that event bus can work in both ways. So in your JavaScript code, you can publish messages to the event bus. And console is the only module in this Rita platform that uses it more for the fun of it than anything else. You don't need to. You could just use socket communications. What's this? Message filer. That is a general purpose thing, listening to the event bus that archives the messages properly, but it's general purpose. Now, this brings us up to a current and trendy, everybody's heard of LAMP, right? Linux, Apache, MySQL, PHP. Well, there's an acronym MEAN. Ring a bell with anybody? Right, let's sort of bring in LAMP up to date, which is MongoDB, the Express web server, AngularJS, and Node. The web server Express is an extension of Node. Okay, those are trendy, and I express caution when you consider using any of those things. You'll see all this work that's been done for the City platform. It's been done in really quite a considered way. What capability do we need? How could we kind of deliver it? Is it worth going slightly off-piste and using technology that's more modern, or if this can be fulfilled with Oracle and Apache, let's just do it with Oracle and Apache, right? It's done in really quite a considered way. Once you hear this, I think get a big vibe that you'd heard it. You hear this kind of MEAN acronym. There will be a risk of people in our industry, they go, oh, we've got to use Node. You know, we should go Angular. You know, because we've all been in that industry where the answer to every question is the name of whatever product happens to be trendy at the time. Okay. So MongoDB. Now, actually, message filer. MongoDB is a NoSQL database. It's perfectly good at what it does. There is a MongoDB Vertex filer, which just automatically files messages from the event bus into MongoDB. So you don't need to write any code at all. And I was aware of that with message filer, but I've deferred. There's no MongoDB in this system, right? It's storing the data in a very, very simple way, even though there's 1.5 billion data points. To connect to MongoDB would be relatively simple, but I've deferred it to avoid this sudden focus on the database. In the same way, when we kicked this off, by the way, a year ago, there's a lot of focus on the app. I'm like, oh, we need an app. Let's build an app. It'll be really cool. Phone gap, that'll work. It's got to run on the Windows Phone platform. You get all this kind of nonsense, frankly, because people are focusing on the bit they're maybe the most familiar with, whereas in fact you need to take a step back and think about what capabilities do we need. And I've deferred doing those bits to make sure we get the basics right. To the extent now that it'd be relatively easy just to plug in MongoDB to this and start archiving these things. In addition to where the feed handler is storing them in the cache, the message filer is storing them in another data storage, just to plug in MongoDB and have them start being stored in MongoDB would be very easy to do. But I'd much rather have done it when it became really easy to do than at the beginning when I had no idea what we were doing. Feed CSV is a specialist vertical that specifically for storing a feed because if we give it to land economy or geography, they don't want this feed is being given to a variety of people, by the way, including the computer lab. The computer lab just said, just give us the binary, right? It's coming in binary. Frankly, they struggled to unpack this binary. I mean, it's an awkward format. So converting it into comma-delimited ASCII, because that's all it is, bus ID, latitude, longitude, timestamp. It's not rocket science. Just put it in feed CSV. As well as archiving the original binary content. There's no reason for doing it, but actually there's a vertical that does that. What's this? Feed publisher this is a bit like a Lego. This whole system is a bit like a Lego brick. It's kind of the inverse of the feed handler. You receive data from the event bus, and then you can post it on somewhere else, which is what I've actually implemented. So there is a clone of this system. There's a version of the system running under my desk. There's a clone of this system. There's two clones of the system running in the computer laboratory. And they're forming kind of a network in that messages are being forwarded on. So one of them goes pear-shaped. We definitely won't have lost any data because the other ones have been subscribing to it. So you can think of that as an inverse feed handler. Okay, so far we've got the following actors. And you can see they kind of behave a bit like actors. A feed handler just kind of has got a particular job to do. It gets something, it does it, it passes the data on. It defers the storage of the data in the appropriate way to another actor. Okay, none of this stuff I've showed you so far has got anything to do with buses. Right? It doesn't care. None of those modules have any idea what that data is for or how you would interpret it. The idea that you're going to archive it is completely generic. Okay, so we do have some transport-specific verticals, crucially including this thing called zone, which is given configuration parameters of an area of interest, a geographic area of interest, and it listens to these vehicle position events, basically to say, has a vehicle entered my zone, and has a vehicle exited my zone, and if it transited the zone, how long did it take start to finish? And if you can just see that the zone is the little mappy thing drawn in the bottom right-hand corner, it's got an entry and an exit. It's kind of, typically in transport terms, you talk about how long did it take a bus to go down Madingley Road. You're not interested in ones that crossed it from north to south, who were in it for a couple of seconds. Okay, so there's a zone. The zone is kind of interesting in that it receives messages, does some kind of processing, and then produces its own messages onto the Eventbus bus, which is typically many, many fewer messages. It's broadcasting messages saying, a bus has just transited my zone. They happen a lot less often than buses moving in the entire region, right? So there's a compression, but also there's a move up the value stack of how valuable these messages are. Okay, and then I think this is the last module, a vertical I'll be talking about, RITA itself. So we've called the platform RITA, Real-Time Intelligent Traffic Analysis. But when you as an end user connect to the system, you are in fact talking to an HTTP server running in a module itself called RITA, which basically looks at the URL you're requesting, provides you with those web pages, and then subscribes on your behalf to real-time data, or just picks up the historical data and plonks it on your page for you to actually see. So the thing you're actually connecting to is RITA. Should you be interested? This whole thing, by the way, is fronted by Nginx. So as opposed to Vertex itself being the thing that's being hit with a request directly from the end user, that's actually hitting Nginx as a front end, because it gives you some availability benefits. Okay, so I told you Vertex provides non-blocking APIs. I haven't emphasized this item 5 on the non-blocking APIs. We talked about web servers or data or Eventbus. It itself has an API for starting and stopping verticals. Okay? So actually I have a couple of other things going on. I have a thing called a zone manager, which itself listens to the event bus, is listening on an address called, mysystem.manager or whatever, to receive requests. Would you start this zone, please? Would you create a zone with these parameters and launch it automatically? That's what Zone Manager does. So it launches zones. It doesn't know ahead of time what sort of zones. It gets asked to launch a zone. Once that zone launches and you tell it which address you would like, which feed you'd like the zone to listen to, and you tell it what address would you like it to publish its zone completion messages on. It's all quite, the concepts are all really simple, but you can build quite a good Lego set out of it. Okay, so that's the thing, that's a zone manager, and Rita itself can spawn its own feed players and zone managers. Okay, now where I told you that the event bus can span Java virtual machines, it can span real machines, well actually it's quite attractive for planning purposes or experimental purposes, is you can actually spawn an instance of Rita which has its own zone manager, its own zones, and its own feed player, but you've said don't run in clustered mode. In other words, don't broadcast your event bus to any other machines or any other JVMs on this machine. And so what happens is you have actually a self-contained environment, which there's no additional code, it's just a configuration. You've created a configuration which is playing back a feed, running it against certain zones, publishing information, and you can kind of look at it on the screen. That tends to be how I get to look at it at 50 times normal speed. And I can run all the zones, all the vehicles at 50 times normal speed, and it behaves the same, really. But just the dots accumulate faster. So I'm getting near to wrapping up. That is a screenshot from a documentation page that's on GitHub. My ID is IGL20 on GitHub. That is an actual page. So with a bit of luck, you would recognize now that picture. If I'd shown you that at the beginning, you'd have absolutely no clue what I was kind of talking about. But so you've got the feed handler, feed player, feed CSV, message filer, got the console. And this is where, and it fits in that central real-time framework and historical archive section of that diagram. Elsewhere, we weren't kind of quick enough to big up the project. This idea has been referred to as City OS. Cities will become digital, right? And they will rely on a communications fabric. They are a rich source of censored data. And there are projects going on around the world, funded projects, looking at what do we need in terms of a City OS. That was described to me by a senior colleague as content light at the moment. In other words, there's a lot of well-meaning conferences taking place. What are we going to do? And with the best will in the world, that's impacting a lot more geographers and land economists and people involved in that space. And they don't necessarily have the underpinnings. So just before I wrap up, you will now recognize, I think, these screens. So if I launch the console, it's message passing, okay? It's not read a database to say what's up. It is now waiting for messages to come in. They're going to come in. All of them will come in within 10 seconds, because that's the period. And the console's heard those messages, and it's got status up, okay? The time there says it's 11:10, and some of these, I know you can't read green on black, but the time of when they were last seen to be up was 11:14 or 11:12, different varies. And in 10 seconds, they will remain, with a bit of luck, they'll remain green because another message has been received from those particular consoles. The point being, just the way you saw that application warm up, it didn't have to warm up that way. And in fact, I'll show you something slightly different, which is when I show you, let's do this twice. So Madingley Road in. So I'm talking to Rita at the moment, and I've got a URL which says, I'm interested in Madingley Road in, and in fact, that URL has got included on it. I would like you to show me the map. Okay, that was, so it knows with the information it's actually going to give me. What it did, Rita doesn't know anything about that zone. It sent a message on the event bus on an agreed address, which says, do any of you zones out there know anything about something called Madingley_road_in? If you do, could you send me your configuration parameters that define the zone? That data came back. So actually what happened is the Rita web server served the page, and then there was a slight delay while it collected that data from the zone and kind of presented it. So it's a slightly different, it didn't just read the database, package the data up, come back with a snap, and there it was. None of which is massively relevant, because those things you could have done that way. Anything we give the public, by the way, is likely, in the first instance, to be static. But the system has been built to be real-time from the get-go, because that is what makes it extensible. You can add sensor data, you can do all these kind of things. It doesn't mean when Joe Blow wants to say, where's my bus? That person is going to get a static page. This page here, there's the same thing happening. Okay, Rita has said, I've clicked a button which kind of says, I would like to see journey times on Madingley Road. Up to date, I'd like to see real-time journey times, okay, on Madingley Road. Actually what happened is, Rita, first of all, sent a message to this agreed address, which the other verticals are listening, or the other zone verticals are listening to, which says, we've got a user that wants to see the journey times on Madingley Road. Could you, now what the zones do is they cache journey times since midnight last night. They're just keeping it in memory, because there's not that many, it's 100. Let's say there's been 100 completed journeys on Madingley Road. They've cached that in their own memory. It's all been written to disk as well, but when the Rita request comes in, which was Rita is an agent acting on my behalf, it sent a message on the bus, we want to show the journey times for Madingley Road. That zone has said, I've got them. And if I scroll down, this is a long page, if I scroll down here, the first bit of that, I know, you can see this message, this is all for debug purposes, okay? But that JSON is the journeys that have been cached in that zone, and it's written into the screen. So that's exactly the same as would have happened in a slightly different model, which is, I'm not even going to bother asking the zone, I'm just going to read it. I'm assuming the zone has written it to a database. I'm going to read the database, populate the page, and display it. The difference is, the zone didn't actually get a request for the data so far today. It got a request saying, we've got a user interested in real-time journey times. And the protocol, which is very, very simple, is it catches up, first of all. It sends all the journey times it's had so far today. It doesn't need an infinite buffer, it's just a day's worth. And at that point on, I know, and because this is in real time, it is 1:15. That's why the chart stops at 1:15, okay? And if you want to do what I've done, is you look at the screen waiting for the next dot to appear. Okay, so because those dots will continue appearing in real time as they occur. And because I couldn't have been 100% confident I was going to get that on the screen for today in here, you never know. I looked at yesterday, I printed the screenshots from yesterday. So that's Madingley Road in. That's what it looked like yesterday, which is worse than usual. And also, there's two things. Cambridge has a relatively short rush hour, but it can be, but when it occurs, it can be pretty bad. I mean, that's journey times taken on a journey that normally you can see the norm is about 2 minutes to go from one end of Madingley, a bus to go one end of Madingley Road to another, and that was up to what, 15 minutes. Okay, yesterday morning, and last night, you can see when I did it about 11:30 p.m., 11 p.m., something like that. Really what I was doing is I was going to the system, can I make sure this freaking thing is up, because I'm going to do a presentation, I'm hoping to put it up live tomorrow. But that's the graph I saw. Okay, so in my bedroom, I launched my laptop and launched this screen, and it was a real-time screen, but it did what the system did, is it kind of caught up. So I don't know if anybody was going home at 6:15 last night and had to go out on Madingley Road, but it was a bit crappy, not too bad, it's been worse. If I show you the chart when the car caught fire on the M11, that is a horrendous chart. Okay, but that's still not pretty good. All right? So you are now expert, aren't you? Thank you very much. Any questions? Rob?
So,
I can repeat. It might be easier if I repeat the question. What do you think? Yeah, I'd rather, yeah, because it is. Yeah. Yes.
when you spawn these verticals, do they have a way of registering with each other? Is there some sort of central registry that allows them to respond to other verticals? How does that?
No, the one mechanism is the event bus. So what you would do, because in one line of code, you can send it. There's two. It's very elegant and succinct. This library. You've got two commands for the event bus. I think one's eventbus.send and the other one is eventbus.broadcast. The only difference between the two, and then you give it the address on the event bus you want to send it to, which isn't the address of an endpoint, it's the tag that's associated with the message when it's sent out. The difference between send and broadcast is, do you want everybody to get it, that's broadcast, or do you want Vertex to take care of only, if you do a send, only one vertical will receive it. Okay? You can launch multiple verticals that would have been listening for it, but you've decided in your own design, I don't care who gets it. So let's say you want to do a database store or something like that. You don't care which of those two verticals does it, as long as one of them does. And that gives you HA. But exactly as you describe, you saw the way my console is working, for example, is when verticals, actually this is an ongoing basis, but when they wake up, they send a message actually saying I've started. But it's something I put in the code. And there's a bit of a nuance in that if you extend the event bus to the browser, some of these things you've actually defined your own constants. So if I've got a vertical started message or something, I give that a message. I've got this thing called message type. Okay, and that's a Java constant, and I've got a Java class which defines these constants so that Java's doing a brilliant job, as I was helped to do by Dean, or instructor I ought to do it with Dean, is I'm using this constants class, so it gives me type error checking and that kind of stuff. In theory, that wouldn't extend to JavaScript in the browser. So in other words, from the browser, I kind of say, you know what I want to do? I want to do a zone update request. Because I'm going to send that message and says, does anybody know zone with this ID? That, again, is using a constant. And what I did is I added to this constants class a convert it to JSON, because it's only a linear list of things, right? Convert it to JSON method of that class. And when a JavaScript client connects, I'd call the Java class, call that, convert yourself to JSON, and I send that in a message, actually, to the client. And the client then embeds, it decodes the JSON and comes up with a set of constants. And so I've only got one set of constants, and they're actually defined in a Java file. So think simple is the model.
So you said there's this initiative, CityOS. Is it national, international, and will Rita have a future in CityOS?
There's a global. There's a three-cornered international project with a major city where there's a project that Cambridge University is contributing to. That piece of work, which is City of the Future. There's City of the Future projects going on all over the place. There isn't a huge amount of technology underneath it in the main. This particular three-cornered love triangle, it's structured into sort of 7 tiers of the sociological impact of urbanization. There's all this. When you get down to the bottom, there's City OS, and that's where the content light comment arose, because that piece of it, we are leading the way. Other countries in the world, I've got a foreign trip in November, somewhere else, where they have heard what we are doing. And it's a bit of a target-rich environment, that if you think you can do something fairly good, we're aiming to be great, aren't we? We're trying to build something that has got longevity to it, but it's cleverly done. And I think if you took Vertex itself, one of the clever things about it is that it's simple. And what I've described here, what I hope it leaves most of you with, is the idea, you could do this, I hope you don't ask me, have you done this, have you done that, have you done that, because there's a million things we haven't done. The people that contributed to this effort has been primarily me, writing most of the code, and then there's a couple of guys in the computer laboratory that have contributed pieces, and also I've gone to see them and discussed those bits we're actually going to do. And then some of you in the room will know that I've kind of asked questions occasionally. What do you think I should do with a particular thing? And I tend to get an answer. So that's, that's the effort that's gone into here. But you can look at it. There's lots of things you could do. There's something I definitely want to do, and I've been cautious about. Well, you could persist this data in MongoDB. Yeah, I know I could do that, but what's that going to, what is that? There's not much I can't do. And in fact, a long list of functional things we could do are not dependent upon doing a very easy thing, which get this thing into a NoSQL database. Whether it's MongoDB or not, I don't think it would be, actually. Aren't dependent upon that. And the examples include, it will be good, I've been cautious to do it, but present a very small number of end-user web pages that first of all just give you the status of transport in Cambridge. So it could look a bit like the tube map, and it kind of says Hills Road good, Madingley Road good, Trumpington Road not so good. And we try and do that in an intelligent way. I've got projects in discussion with the computer lab about how would you intelligently purvey this information. And then the next thing up from that is where we have zones. We could have routes, because this is bus data. We could have routes, and that is another vertical. You've got a route's got its definition, but crucially its definitions, the things it can now know about in the system is richer than the things that the zones could know. The zones can only know about positions, because that's the only thing downstream of them. By the time you're looking at routes, you can say, what zones does this route care about? But also, it can detect what specific vehicles are on its particular, it can be tracking both how an individual vehicle, it only cares about the vehicles on its particular route, right? So you're not looking at all 1,000. And it only cares about certain numbers of zones, presumably. But you could write a vertical that told you something sensible about the Uni4. You absolutely could. And those are the kind of things we want to just stay focused and keep doing. Anything else? Chris? You must have. You're looking... This is all rubbish. Well, you should be thinking, this is all rubbish, isn't it?
I was going to ask how reliable, how well behaved have you found Vertex? Exploded in a shower response onto you, and if so, why?
No, it's been running. Vertex itself has been running for really quite a long time, and it's a library. It's not a server.
How reliable are the applications? How reliable are the systems built with it?
Yeah, I mean the feed handler hasn't stopped since June last year, and it's the main developer of Vertex is a clever individual, and it's easy to make something clever and complicated, and it's a smart platform. What's more important, because you can have a whole load of it's a library you call, so really what you're saying was, did the Eventbus work? Did the HTTP server work? Well, they have so far. But a lot of your code, like say you're writing to Postgres, all your code in the Postgres writing and the JVM, and is pretty mainstream. So it's not bad. More important, so I've had, in that time, I've had one core dump. And there's a thing called Jackson, which parses JSON in Java. Okay, well that's what caused the core dump. So it wasn't actually Vertex. The system crashed, but it wasn't actually Vertex. It was in this Jackson library. But I suppose, if you're using, if I wasn't using Vertex, maybe I wouldn't be using JSON. But if you're communicating with a browser, you really need to be in JSON, as a commonly understandable format. It's like the CSV of the 2000s. What's more important is that the modular structure of your code. If you've got a request-response thing, that is one vertical. Right? I'm not suggesting you take we've got a system where job applicants can propose somebody else to do them a reference. That person gets an email with a link to a web page that they fill in saying, this guy sucks. That would be one vertical, or there'll be a page being served by an existing vertical. I'm not saying that system would somehow expand into all these different verticals. But when you have built a platform using these objects. And for that, by the way, I wouldn't bother using Vertex. There's nothing in Vertex that would give that system anything. It gives you a way of thinking about the system where you tend to design it to be robust, with a vertical can fail, and typically it will be, it's in Java, it's on a JVM. That JVM, the feed handler is in its own Unix process, on its own JVM, and I've got 3 of them running on 3 different servers in different buildings. It would be hard for something else to, if some other bit of this platform crashes, it would be extremely hard for it to somehow bring the feed handler down as a result of some other part of the system. So that's a robust aspect of this style of design, which isn't anything to do with the quality of Vertex code. It's just, you tend to build this thing in a modular way.
I guess the message bus is the core bit. If that were to misbehave,
Yeah.
or if the communication between 2 actual machines
Yeah.
of those messages was to break down, then
Yeah.
the functionality of the thing you built would
Yeah.
be
And I think
fairly compromised.
I would be. I think if I were in a financial institution where there'd be a lot of concern about this kind of thing, is because Vertex has got a non-blocking library for message MQ. If I wrote a feed handler that's receiving price feeds, I'd be pumping it out to, rabbit MQ. Sorry, forgive me. But I'd be pumping it out to production grade messaging platforms, which effectively will be a plugin. It will be a plugin replacement for the Eventbus. Number one. Number two is in terms of production stability. Like I was saying with the end user, if the end user wants to click a button and go, "Where's my bus?" I wouldn't write that in a way that's got the event bus propagating. For that normal member of the public end user query, it would probably be a database request that would render a page that they get. Whether the event bus is there or not wouldn't make a huge amount of difference.
But what about scalability? So if you threw out the event bus or its successor, telemetry from your Nest controllers, from Fitbits and wearables for a smart city OS.
Yeah.
How far would that
Well, nothing else would cope on the scale that this will cope, right? So a laptop can cope with hundreds of thousands of event buses messages a second, because it's designed to be really lightweight. There is also the characteristic that makes it much, much easier as with financial systems. Worst case, you can afford not to get a message if you miss if you miss a tick. But as long as that wasn't the last one the bus ever sent, because you do anyway. A bus that's trogging around, it goes halfway around Cambridge, there's no mobile phone signal. And you don't get an update. And you would see there's error checking. Like in a zone, when a bus enters the zone, what the code actually does is it checks the time, because basically it's detected there's a data point outside the zone, there's a data point inside the zone, the 2 consecutive data points. It draws a line between them and says, did it enter where I wanted? It also checks what was the time of these 2 data points, because there's pathological cases where it was just outside the zone at 6 a.m. The next data point you got was at 4 in the afternoon. And as coincidence would have it, because you may lose data points. And that makes, so what's in this system so far is working on that assumption. You can afford to miss data points. Vertex itself is not queuing data points. If you do, you're opening up a whole other kettle of worms if you're queuing, because if you've got a thing at one end, it's not as quick as the thing at the other end. You have to work out how to do distributed flow control, and it can get nasty. Whereas you radically simplify that problem by saying not getting a message is not the end of the world. And actually, what's been done so far, it's not a user that's kind of looking at a bus. They could potentially be given out-of-date bus information by a small amount, but they could have been anyway if that bus had been.
We have to stop. We're out of time.
Wonderful.
Thank you very much.
Thank you.